Hey everyone, this is Luke Merrick. I'm a data scientist with Fiddler Labs. I'm here in my hotel room at the NeurIPS conference, and I wanted to share with you a couple of my thoughts from the conference yesterday and some really cool workshops that were presented. So first off, Emti from the VOGN Institute presented some fascinating work on applying Bayesian principles to actual deep learning algorithms. So a lot of Bayesian deep learning efforts out there have been focused more along the lines of kind of creating deep learning models that follow this Bayesian structure. Emti's work thinks more at a high level around what are the principles of Bayesian learning and how can we bring those principles to just kind of sprinkle them into existing deep learning algorithms. So what we get is an ability to use something that's fairly Bayesian that runs, within a 2x slowdown from normal, GPU optimized implementations on neural networks that can learn ImageNet, your state-of-the-art models just as accurately as stochastic gradient descent. In fact, they beat the Atom optimizer that they were comparing to as a benchmark in terms of speed. But then also, because it's Bayesian, they have a measure of uncertainty. They know where the model is uncertain and wrong, and so they were able to show their calibration between their uncertainty measurement and the actual class outputs of the model of a traditional model, that theirs was much better. And this uncertainty is, it's really exciting to our work at Fiddler because we want to help people understand, where their model is unsure, and our hope is that this type of Bayesian principles will be able to trickle into products and techniques that we can work with customers to build and all of that. Now, after this presentation, there was a fascinating one on interpretable comparison of distributions and models. Now, this was given by Widawat Yikutum, Douglas Sutherland, and Arthur Gretton, and was a very interesting tutorial because so much of the work is inspired by these generative models, GANs, where you have this adversarial relationship. You have this discriminating model that needs to tell if some sort of example, often an image, is pulled from this distribution of the data, or it's completely made up and fake by the generator model. And so you're simultaneously training something that can discriminate between two distributions. Sometimes you use a model for this in GANs. There are also variational autoencoders. There's a bunch of different techniques, but they come down to this discrimination between two distributions. Now, we don't work a lot with generating data and generating images, but where this comes into practice for us that's very fascinating is we have to measure this divergence between distributions for cases where customers have a model they're using in some application, and then something happens in the real world and things change, and they're worried that maybe their data is changing. So maybe they start business in a new region, and maybe people in that region are not the same in terms of the data they're putting through their machine learning systems, and they want to make sure nothing breaks. So what was cool about this is not only are there a bunch of techniques for this high dimensional data case where it becomes very challenging to kind of confidently determine if the distribution is shifted and how much it's shifted, but some of these techniques really focus on the interpretability of that shift and being able to point out exactly where that shift happened, finding examples that are most different from the normal distribution of each side. And we hope that we can leverage some of this work in our own product as well. We're already scheming about a lot of ways. So, there's a lot more conference to go, but I wanted to just check in with these two examples. I highly recommend you look at the work of Emti on Bayesian principles in deep learning. He's got a long form paper that he's developing. There's already a 6-page draft up on his website, as well as Arthur Gretton and the others in that tutorial presenting a lot of interesting ways to measure and discriminate between often high-dimensional, complicated distributions of data like we see in the real world in a lot of these applications of deep learning.